Okay, so picking up where we left off last time, we do not test blocks. Um, Blocks are kind of, you should think of them as intertwined with those units, those experimental units. There needs to be differences, or there should be differences between the blocks. If there's not, then perhaps our reasoning was incorrect, or with our particular data setting, it just didn't pan out, and that's okay. But there should be differences between the blocks. Um, we did not assign blocks to units, and they were not randomly assigned. Hence, we do not make any conclusions about those differences between the blocks. Okay? The software, unless you're using SAS, the software isn't going to distinguish between a blocking factor and a regular factor, so it'll just test, but you just ignore it. It's no biggie. Um, However, for unbalanced data, you look at your treatments where they're adjusted for blocks. The blocks are always in the base model for any treatment factor, of course. And For balanced data, you don't need to worry about this, though. You don't have to have any adjustment for the treatments because the blocking and factor for your treatment are going to be orthogonal in that case. Okay, so when I always used to report randomized complete block designs, I'd always compute a relative efficiency. What is that? It's kind of a little bit of a test to see what effect the blocking had. Okay, so if the error variance increased a lot by taking out the block, then we know blocking was effective. Or I could have said that the other way. If the error variance decreased significantly by including the block, then we know blocking is effective. And that relative efficiency is a measure of that. Using that same universe of units, by what factor would we need to increase our sample size to get that same power in a CRD that we can achieve using a randomized complete block? I like relative efficiencies. I don't see people reporting them, but I think they have a lot of relevancy anytime you use some kind of efficiency measure in a design. And so I always like to compare it back to maybe the simplest CRD and see what my relative efficiency is. So, um, to get this relative efficiency, we're going to just estimate the error variance using the CRD instead of the randomized complete block, and then compare that. And here's our calculation. If we estimate the variance, the error variance by MSE in a randomized complete block, then we can estimate the error variance for a CRD using this kind of a formula. Notice that this is an average of your mean squared error and your mean square block, and it's just a weighted average, though, because it's weighted by the degrees of freedom associated with each of those effects. Typically, this is going to be less than the MSE you would get if you just re-estimated the model without your blocking factor. But I guess it's conservative in that sense. Okay, so once you've computed using this formula, once you've computed that variance, of course, we have an estimator of this from the MSE. Then we can find our degrees of freedom for the randomized complete block, or degrees of freedom for the CRD, plug those along with the variances into this relative efficiency. I always write RE, and that just makes more sense to me. You can write E or RE, but I do like his notation here because it reminds us what it's for. It's for a randomized complete block to a completely randomized design. And so we get that ratio. So notice this, presumably this variance for the CRD is going to be bigger than the variance for the randomized complete block, but if they're kind of commensurate, this will be really, really close to 1. And then we'll have something very close to 1. An interpretation here. Oh, but let me finish my thought there. So it's close to 1 if these are pretty commensurate, but if this is a lot bigger because the blocking really improved efficiency in your design, then this will be something big, much bigger than 1. So for example, if your ratio ends up to be 1.7, just picking a number out of the air, then you would need 1.7 times as many units in a CRD to achieve the same power you get using a randomized complete block. So that's nice. And say you get a 5, then you'd need 5 times as many units in a CRD to achieve the same power as a randomized complete block. That's kind of an extreme example, I'd say. All right, so that finishes up randomized complete block designs, and now everything else is just going to be a variation on this. So blocking is an effective way to take care of this extra heterogeneity, extraneous variation, as Gary says here. But what if we have more than one source of extraneous variation? For example, you're growing flowers. The amount of light and the drainage are two factors that perhaps you can't control, so you don't want to include them for optimizing your growth conditions for your flowers. But you need to control for them in the experiment. So these would be 2 blocks, 1 block for light, 1 block for drainage. All right. Another example, gender and blood pressure in cardiac trials. So obviously we would not want to certainly not make gender a factor, because we want to be able to treat both women and men, and we don't want to say, well, it's better to be a man and do this for these cardiac outcomes. It doesn't make sense. So we want to block for gender. That's an obvious one. Blood pressure is probably also a good one to block for, because there's all kinds of different natural levels of blood pressure that may or may not be able to be changed significantly. Driver and environmental conditions in miles per gallon trials. Okay, again, driver, environmental conditions, I would say, are definite random factors, hence blocks in this case. Okay, so if these 2 blocking factors happen at once, we do something called a Latin square. The Latin square is a classical design for blocking when we have, again, these 2 sources of variation. It's kind of a neat design. It creates these nice little Latin squares that are fun to work with. My first book had lots of Latin squares in the back of the book that you'd look up to see how to randomize. You have G squared units visualized in a square pattern. These units are the same, are in the same row and are all in the same block based on a first source of variation, and then those units in the same column are all in the same block based upon that second extraneous source of variation. We're going to see one of those squares in just a second. But we make sure in these Latin squares that the G treatments are randomized, so each treatment occurs once in each row and once in each column. So it can be a little tricky. You can get Latin square designs in R. We used to always use charts and tables in the back of books. They happen to be called Latin squares because the treatments are represented by Latin letters. And that's classically what was done. So here's an example. If you ignore the columns, a Latin square is just a randomized complete block in the rows. So notice, here we have levels A, B, C, and D. Then B, A, D, C, C, D, A, B, D, C, B, A. So that's just a randomized complete block. Similarly, if we ignore the rows, then a Latin square is just a RCB in the columns. Notice we've got A, B, C, D, B, A, C, D, C, C, D, A, B, D, C, B, A. Did I say that right? And so randomizations occurs on both your row and your column. That's why I said the design can be a little tricky, because you got to make sure it's kind of like a Sudoku a little bit, right? I think that's why I like those puzzles too, is I always liked putting together these Latin squares. Typically randomization, if you're going to have to make one up yourself and not rely on a table or a computer program, you take a square from a table of squares on the back of the book, you randomly permute the rows and the columns, and you randomly assign your treatments to the letters. It's not as random as you randomize subject to treatment levels kind of thing that we've done in the past, but it's a lot simpler and pretty good. Okay. You can actually, there's a program that I've used. I can't remember the code off the top of my head, but I've also done the randomization in R. You just load a package and it'll give you the pattern to use. So that's pretty easy too. Here's the model. Alpha and beta are our blocking factors. Is that right? It's not clear to me. It doesn't really matter now, does it? Let's call alpha our factor. Okay, beta and gamma are going to be our blocking factors. Again, doesn't matter, just Greek letters. But notice everything's additive. Again, we might need to log transform to make this make sense with the data. If you got unbalanced data, make sure your treatments, your alpha effects are adjusted for the blocking factors. This can be done. We can look at this in class. Okay. What if we need more data to achieve some level of power that we want? You have to think of these rows and columns as fixed effects. Or if you think of them as fixed effects, then we would have G minus 1 and G minus 2 for our error degrees of freedom, right? Because we have G levels. Once one level gets taken away, we have then 2 levels that are accounted for entirely in the other. That's not a lot of degrees of freedom for error. I mean, imagine if this is 4, then we've got 3 times 2, 12. I'm sorry, 6. I did my math wrong there, didn't I? 4, because 4, yeah, 3 times 2 would be 6. This is not a lot of degrees of freedom for error. So we'll often replicate those. So we'll use multiple squares with the same level sets of treatment. So we get replication of Latin squares. This I saw all the time when I was at Oklahoma State. Suppose we have R squares to study J treatments. All squares will have row blocks and column blocks. And then the issue is whether we get those same row blocks or different row blocks for those replications. Okay, so here's an example. We got 3 squares, G equals 4. So 4 squared, if we only did one Latin square, we'd have 4 G squared observations, right? Where did I get that? Right there. We only observe G squared of our combinations. So we'd have 16. 16 times 3 is 48, of course. And so that's how we get our 48 total units. Here's our levels for treatment, the gasoline additive. Our response is going to be the emission level. Our row block is the driver. Our column block is the car. So we could use every square uses different drivers and different cars. This is one option for us. This is a mean plus treatment plus square plus car nested in square because the car is going to depend on which square you are in. But the driver also depends on which square you're in. So these effects are nested. So there's going to be G minus 1 for your treatments, of course, R minus 1 for your square, and then R times G minus 1 for your cars within square, R times G minus 1 for your driver within square. This is one option, not one I would prefer. If we did it this way, we have cars 1 through 4 here, 5 through 8 here, 9 through 12 here, and the blocking is also done by driver, 1 through 4 here, 5 through 8 here, 9 through 12 here. So it's an option. Option 2, every square uses the same car but different drivers. Okay, so here we need to think about the mean plus treatment plus square plus car driver, where driver is nested in the square. Okay. So let's look at this one. So we've got cars 1 through 4, and then the drivers nested within square. This one to me is a lot more direct and simpler. Okay, we're going to have to stop there. I just looked and we're nearly out of time, so we'll pick these back up next time.